get the dominant coupled modes. So we can simplify this problem in terms of m equals to 1 and n equals to 1. That turns out to be a 1-to-1 interaction. Similarly, for 2-2 interaction, it looks like this. So the advantage is that this general problem can be further simplified if we go like this lower order, sufficient amount of accuracy. So for 1-to-1 interaction modeling, we can write down like this way. And the coefficients can be expressed in closed form like here, you can see here. So for identical elements, it's interesting to show that this will be either +1 or -1. So that actually matches with our physical observation. We see odd modes and even mode generation. If both this is 1 + 1, then it's a even mode or common mode. -1, it's a odd mode. Similarly, for 2-to-2 interaction modeling, you can write down like this. So it's a 4x4 matrix where each element is a n by n cube problem. So instead of 2 cube n cube, you can solve a n cube problem, then construct a 4x4 matrix operation. So how accurate is? If you see the 1-to-1 modeling and compare it with the 2-to-2 modeling, you can see we have taken the third order modes to get a better improvement in the accuracy. You can see that it is as we are going towards 2x2 modeling, getting more and more accurate. So the accuracy is not that much prominent there, but there is some examples will show for plates where it is much more dominant. So there is an alternate theory of this TCCM also reported in another work, this one, which provides the coupled eigenvalue like this. So for homogeneous array, you can simplify it in much more way like this. So basic difference of those two, which one is computed first? The first method actually eigenvalues are computed first, next eigenvector. Second one is the vice versa. So you can choose any one of them, both will lead to same results. And some comparison results, we have taken two dipole arrays, 0.5 lambda with the separation of 0.3 lambda, 300 megahertz. And conventional characteristic mode eigenvalues we have compared here with respect to the TCCM using two techniques. We can see both the TCCM technique gives same result. A small difference that is expected because TCCM is an approximate version of TCM. Now, how does the normalization technique matter? First, we have considered the same problem, but we have taken two normalization technique. One is the Harrington's technique, and the one is the max amplitude, current amplitude technique, like this. You can see here for max amplitude, it should be always 1, but for power amplitude normalization technique, it is slightly different. But the ratio of those two coupling coefficients is always constant, means same in both the techniques. The ratio actually represents the coupling behavior. The total current depends on this ratio also. Since it's constant, it will give the same current in both the cases. Now, the orthogonality problem in TCCM is crucial as we show here. So how do we can be sure that this TCCM, since is an approximation, does this maintain the orthogonality? So to prove that, we have to maintain this relation for two coupled modes here. And this is the coupled matrix with the real part. So those two modes can be written using 1-to-1 interaction like this way. Now, if you just consider the very simple one like even mode, odd mode generation in identical array, you can write down the left hand side like this way, just some matrix multiplication will give you this equation. Now we know that this follow relation, these two coefficients follow this relation. So 2 multiplication will be -1, so this will be 0. Similarly, now the plus summation of these two will be also 0. So the orthogonality is also properly maintained. Now how accurate this is with respect to the conventional technique? So we have defined two parameters. One is the eigenvalue error, and another one is the eigenvector error. So eigenvector, we are taking the dp difference here. We can see that for the first order interaction modeling with 1-to-1 for two dipoles, you can see the error pattern looks like this. What error it will look like? If you can think about, remember the modes of a thinner dipole, you can see this is the third mode. So that indicates that the first mode has certain amount of coupling with the third mode. Therefore, if we go from 1-to-1 to 2x2 modeling, where this 2x2 modeling is taking between first and third mode, you can see that there is the error performance is actually improving here. So the improvement is not that much prominent in dipole because it's only the first pair of modes are dominant. If we see for such an extreme case like this non-inhomogeneous array here, can see from from the first 0.1 modeling to the 2 by 2 modeling, the error performance improving significantly. So the theory can be just 2 by 2 approximation lower order matrix problem can be applied to compute both homogeneous as well as inhomogeneous arrays. So this is a huge advantage from computational side, but from application side also it can be useful. Like let us consider one application like mutual coupling reduction. So what does it mean? So there are the two antennas here. We want to reduce the coupling between the second antenna, that is B here. Now, when antenna A is exciting, there is a coupled current in B. Although the B is not actually excited, but due to the coupling between these two antenna elements, there is some coupled current. What will be that coupled current? Using TCCM, you can write down it in closed form like this. That this is the isolated mode of this. You don't have to solve the entire problem, just solve only isolated problem. Get the eigenvector and then coefficients can be computed using this. So now your target will be to minimize that coupled current using certain techniques. So the technique followed here is to put some arbitrary parasitic structure here. We have taken an electric dipole, will optimize the length of this parasitic dipole so that it reduces the coupling here. So for different length ratios of this dipole, we have been plotting the coupled current here. Maximum coupled current here. You can see there is a certain ratio length, that is 0.5 lambda of this value. Coupled current is minimum. So that means that if we put a 0.5 lambda P here, the coupled current will be minimum in these two. So to further validate that theory, we have just put a 0.5 lambda element C here, compute its S1 and S12 parameter. You can see without the element, the coupling, that is dotted line, is very high, and but with this element is going low. So it also has certain impact on the matching here, that is expected because due to the coupling, the eigenvalues are being changed from the isolated value. Eigenvalues control the matching. So that's why some minor effect is here reflected in S1 on parameter. But the total coupling depends not only purely on S1 or S1, so rather it depends on both the parameters as shown here R12. So you can see in the last picture that we have defined parameters which consider both the port-to-port coupling as well as the self-reflection law. So it is also going deeper with this element C. In such a way, one can control any arbitrary antenna array coupling in a parasitic structure. The geometry of parasitic structure can be optimized, not for electric dipole, it can be any arbitrary structure. Simply we have considered electric dipole here. Some possible scope of application, one is this coupling reduction as we discussed. Similarly, for wireless power transfer, we want to increase the coupling between two elements. Other thing is PCB design where there will be coupling between the upper layer and the ground layer. So other thing is like you can use this TCCM current to compute your desired current density or desired pattern synthesis problem. Similarly, the coupling between two modes can be successfully used to control the bandwidth, because bandwidth is dependent on the coupling of multiple modes. So that's pretty much all we have today.